Virtual machines, VMs, represent one of the foundational elements within Microsoft Azure. By emulating hardware in a software-defined environment, VMs allow administrators to deploy and manage operating systems and applications without concerning themselves constantly with physical infrastructure. In the context of the AZ-104 certification, VMs serve a crucial role in accommodating various workloads, from web servers to development environments. VMs are highly customizable and can be created with different images and configurations. They integrate with existing Azure services, such as networking resources, storage accounts, and monitoring tools, to ensure seamless operation and enhance resilience. By leveraging capabilities previously studied, including the interpretation and modification of Azure Resource Manager, ARM, templates, or bicep files, administrators can create well-structured deployments that evolve efficiently with organizational needs. This understanding underpins the successful deployment and management of corporate solutions, making VMs an ideal starting point for mastering Azure's compute services. In Azure, virtual machines function as versatile building blocks for diverse scenarios, helping organizations migrate on-premises workloads or spin up new solutions. They provide more granular control over dependencies and configurations compared to platform-as-a-service offerings. By combining a VM with Azure networking components, such as network security groups, NSGs, load balancers, and virtual networks, administrators can define secure environments that emulate or enhance traditional data center architectures. Integrations with Azure's monitoring suites, such as Azure Monitor, facilitate detailed performance tracking, while Azure Backup ensures business continuity by safeguarding crucial data. From development testing to production workloads supporting global end users, VMs deliver reliable compute capacity. Previous topics in this course highlight how to manage VMs using template-based deployments. Whether one applies ARM or bicep templates, the capacity for repeatable, automated deployment is enhanced. This level of consistency supports governance policies, making it easier to align new deployments with organizational standards. Creating a virtual machine in Azure requires consideration of various factors that affect both performance and cost. Before initiating a deployment, it is essential to identify the intended workload, e.g., web application, database service, or testing environment, and the corresponding computational demands. The choice of region becomes vital in optimizing latency, meeting data residency requirements, and complying with regulatory laws. Furthermore, administrators must explore pricing tiers, including pay-as-you-go, reserved instances, or spot instances, to manage the budget effectively. Network configuration typically involves assigning subnets within a virtual network and attaching network security groups to enforce consistent traffic control. Another key concern involves identity and access management, such as determining who can modify or access the VM post-deployment. By carefully planning these aspects and leveraging ARM or bicep templates for resource creation, organizations can architect scalable and secure infrastructures that align with broader cloud strategies. Choosing a size for your Azure VM is a balancing act between resource needs and financial constraints. Azure provides distinct sizing families tailored to specific workloads. General-purpose instances, such as the B Series, suit small web servers and development tasks, while compute-optimized F-Series VMs focus on CPU-intensive operations, including batch processing or analytics. Memory-intensive workloads may benefit from the M or E Series, used for large in-memory databases or high-throughput applications. Meanwhile, GPU-enabled instances serve graphical rendering and machine learning requirements. During the selection process, it is important to scrutinize the vendor-supplied compute units, CPU architecture, memory allocation, and input-output performance. Additionally, administrators should consider the cost implications of each option, especially for production environments that must remain available at all times. By aligning resource usage with the application's demands and utilizing capabilities like auto-scaling, organizations can keep infrastructure overhead manageable while still providing optimal performance for users. Azure provides a wide range of storage solutions to support virtual machines, offering both managed and unmanaged disks. Managed disks simplify administration by automatically handling storage account, provisioning, and replication. Administrators can choose from standard HDD, standard SSD, and premium SSD tiers, each providing distinct performance levels and cost structures. The choice often depends on the throughput and latency needs of the hosted application. Advanced features, such as Azure UltraDisk, offer extremely high IOPS for mission-critical databases or transaction-heavy workloads. Data disks can be attached to accommodate growth in storage requirements, separating OS operations from application data. Backups and snapshots further strengthen data protection strategies, allowing quick recovery from unintended changes or system failures. In alignment with previously studied deployment methods, admins can define disk sizes and types within an ARM or BICEP template, ensuring standardized storage configurations across multiple deployments and throughout the environment's lifecycle. Networking is integral to functional and secure Azure VM deployments. Each VM resides in a virtual network, which isolates traffic and segments resources. Within that network, subnets can enforce logical separation for front-end, application, and data tiers. Network security groups, NSGs, define inbound and outbound rules at the subnet or NIC level, controlling access to services and mitigating external threats. Administrators also deploy public and private IP addresses to establish communication channels for end users and internal services. Advanced network configurations, such as Azure Load Balancer or Application Gateway, balance traffic across multiple VMs, ensuring high availability and efficient responsiveness. By referencing these configurations in a single ARM or BICEP file, one can replicate and scale consistent network topologies across multiple environments. Successful management of these network components underpins reliability, security best practices, and future expansion while providing an end-to-end approach to resource synchronization. Determining how users and applications reach your VM is a critical design consideration. For workloads that require public-facing endpoints, such as web servers, redirecting traffic through a public IP address or load balancer ensures secure and manageable external access. Network security groups can then specify which ports, like 80 for HTTP or 443 for HTTPS, are open to external users. Conversely, private or internal VMs might only be accessible over a site-to-site VPN or express route connection, maintaining confidentiality for back-office systems. Administrators often set up bastion hosts or just-in-time access to limit direct exposure of administrative ports, substantially reducing the attack surface. By codifying these configurations within an ARM or BICEP file, the environment remains reproducible and quickly adjustable to evolving security mandates. Understanding these access mechanisms aligns with broader Azure governance and compliance efforts, helping maintain a consistent and secure approach to network traffic throughout the cloud infrastructure. When creating a VM in Azure, administrators can select from a wide variety of marketplace images, including popular Linux distributions and Windows Server editions. Each image arrives pre-configured with an operating system, potentially even containing pre-installed software tailored to specific solutions. The choice between Windows and Linux often hinges on application compatibility, licensing considerations, and an organization's internal expertise. Custom images can also be created and stored in shared image galleries for scenarios that require organization-specific configurations, security baselines, or specialized toolsets. Whether using a base OS image or a custom solution, the final deployment can be encapsulated within ARM or BICEP files, ensuring that each new environment adheres to the same foundational configuration. This approach simplifies patching, versioning, and testing, as administrators can systematically adopt updated images while retaining consistent resource definitions across multiple subscriptions or regions. Azure Resource Manager, ARM, templates have been introduced earlier in this course to facilitate consistent provisioning of Azure resources, including virtual machines. In the process of creating a VM, administrators define the desired properties, such as size, region, networking, OS image, and disk configurations in JSON format. By deploying the ARM template, Azure Resource Manager orchestrates the creation of each resource in the correct order, handling dependencies automatically. This approach also helps embed best practices and security standards within the template, preventing errors that may arise from manual configurations. Moreover, ARM templates can be version controlled, tested, and reused, laying the foundation for infrastructure as code practices. This course emphasizes the ability not only to interpret existing templates, but also to export and modify them, ensuring that administrators are equipped to adapt deployments to new requirements. By harmonizing these principles, VM creation becomes more streamlined and consistent across environments. Bicep represents a domain-specific language that aims to simplify the complex structure of Azure Resource Manager templates. Instead of writing long JSON files, users can create more concise and human-readable .bicep templates that compile into standard ARM templates. This is particularly beneficial for creating VMs, as administrators can describe parameters, variables, and resource configurations in a friendlier syntax. Bicep also supports modularization, allowing repeated patterns like VM definitions, network settings, and associated policies to be encapsulated for reuse across multiple projects. By leveraging the benefits of Bicep, organizations can keep large-scale deployments easier to manage and review. Administrators can convert existing ARM templates into Bicep and vice versa, enabling a gradual transition to this more streamlined approach. This complements the broader infrastructure as code philosophy covered in previous course topics, allowing teams to maintain version control, adhere to security baselines, and adapt to shifting organizational demands effectively. While template-based approaches are efficient for repeatable deployments, the Azure portal remains a practical and user-friendly method to create VMs, particularly for initial testing or quick proof-of-concept scenarios. To create a new VM through the portal, admin sign into the Azure portal, navigate to the virtual machine service, and click Create. They complete the required fields, including the subscription, resource group, VM size, OS image selection, and administrative credentials. Optional configurations can specify advanced networking, disk encryption, or the placement of the VM in an availability set. Once submitted, Azure's Resource Manager orchestrates the creation process transparently, and within minutes, the VM becomes accessible for testing or production workloads. For many organizations, this approach serves as a starting point, laying the groundwork for adopting ARM or Bicep templates when demands scale. It also provides an interface to visualize and understand the relationships between different resources. The Azure Command Line Interface, CLI, offers a scriptable alternative for deploying resources without navigating the portal. Using the Azure CLI, administrators can define parameters in a command sequence or script. For example, a VM creation might resemble bash AZ-VM create / resource group my resource group / name my new VM / image Ubuntu LTS / size standard _B2S / admin username Azure user. This approach centralizes essential settings like VM size and OS image, while automating tasks, e.g., generating SSH keys if none are provided. Administrators can control advanced configurations, including attaching data disks or specifying virtual networks, with additional parameters. This completes more complex workflows or integrates into DevOps pipelines seamlessly. It also provides a quick way to validate template-based configurations, as one can manually run a few CLI commands to confirm environment behavior before embedding them into ARM or Bicep templates. Once a VM is operational, organizations often require mechanisms to manage, optimize, and scale it. Azure provides tools like Auto Shutdown to minimize operational expenses and Azure Monitor for tracking performance metrics, e.g., CPU usage, memory, and disk I/O. Scaling typically involves placing VMs in availability sets or virtual machine scale sets, distributing workloads across multiple instances to preserve high availability during maintenance or unexpected outages. Extensions can be applied to VMs for tasks like automated patching, security scanning, or specific configuration scripts. By including these parameters in ARM or BICEP file definitions, administrators standardize new deployments and ensure they align with organizational compliance rules. Auto-scaling policies, governed by CPU thresholds or queue lengths, allow the environment to respond gracefully to fluctuations in demand. This framework of integrated management options underscores Microsoft Azure's approach to facilitating robust, adaptable, and cost-efficient hosting solutions for diverse enterprise and application scenarios.